So the standard enthalpy of formation was the amount of energy that you either have to put in or the amount of energy that you get out when you generate 1 mole of substance from its constituent elements in their naturally occurring state. And just before we broke for fall break, we kind of said, well, here's a nice simple one that we don't have to balance an equation for. But if you wanted to make carbon dioxide, you would take some carbon in its naturally occurring form. So this would be graphite. Everyone's writing with graphite right now. That's the mark that you're leaving from your pencil. The soft gray thing in your pencil is graphite, it's carbon. And we would react it with oxygen, not an oxygen atom, not a pair of oxygen atoms, but a diatomic molecule, 2 oxygen atoms stuck together as a gas, the way that nature delivers it to us. 21% of the Earth's atmosphere is O2 as a gas, and then it would make carbon dioxide. Okay. And the delta HF for this is negative 393 kilojoules. Delta HF change, delta, H is heat or enthalpy, the German word for heat. Subscripted F is for formation, and then superscripted 0 is at standard conditions. Standard conditions for us means 25 degrees Celsius, 1 molar solutions, 1 atmosphere. The amount of energy that we had to put into this planet to generate the carbon was 0, because it's in its naturally occurring state. So by definition, we didn't have to try. Cost us no energy. We get no energy out, we put no energy in. It exists already. So elements have standard enthalpies of formation of 0. Okay, that's a combustion. Combustions are always exothermic. Our energies have a magnitude, how big the number is, a direction. This energy is being given out, a negative number, and a unit. Most of the energies that we're going to see, by the time you can move the increment on the thermometer, you're in the kilojoules, you're in thousands of joules. But it is possible that somewhere in the textbook they'd give you an energy in joules, and then another one in kilojoules somewhere else. You just make sure that they're both in the same units. Okay. Okay, we did say, while this is up on the board, let's just do a couple of other things that are just kind of definition-wise. That if you were sitting around a campfire and you were cold because there was only 1 log on the fire, well, why don't you just burn more fuel? If that's the amount of heat given out for that reaction, as stated, this number is twice as big. That's 796. Okay. And the other thing. Did I do this? I didn't put a 2 there. Make sure there's a 2. If you flip that reaction around so that everything that was a product is now a reactant and everything that was a reactant is now a product, what happens to the enthalpy change? I'm going to take the F off of those two because this one meets our definition. These two don't. These are just enthalpies for a reaction. They're not enthalpies of formation anymore because this is 2 moles and the definition says make 1 mole. And then this is backwards. Okay. So you can actually write Rxn there. That just means this is the energy for that reaction. And although enthalpy changes are usually written in kilojoules per mole, if we're writing one just for a reaction, it's only in kilojoules. Because that's the amount of energy for the reaction that you've written. This is the amount of heat energy given out for that particular reaction. So we don't write the per mole at the end of it. Okay. All right. So we have a worksheet. The first 6 questions on that worksheet were Hess's law. Here's something else. Mix and match those reactions to get to the answer that you're looking for. The last 3 questions are about standard enthalpies. Okay. So we have a direction, a magnitude, and a unit, and we see that they're additive. If I just add another one of those lines to itself, then the energy gets bigger. And that they're directional. Then if I switch it around, it goes from being a negative number to being a positive number. And because this is such a simple definition, it means that whatever it is that you can think of, somebody's already done this experiment. They've already made it and figured out how much energy has to go in or comes out. And it's all in the appendix. So there's an appendix in your book. It's called Appendix C. And it's just full of numbers. And these are the names of different chemical substances. And then here is the enthalpy of formation under standard conditions. And because those numbers are already made, this table is made for us, we can figure out, I could figure out this reaction without really having to do it. That's what the last 3 questions are. So I'm going to put one up on the board, and then we're going to figure out how to do it. Which one am I? Let's pick one. Let's do question number 8. Question number 8. Basically, the instruction is use the appendix, use the table to find the enthalpy for this reaction. Here's a couple of aluminums and an iron oxide, and they're going to make an aluminum oxide. So 2 aluminums plus an iron oxide makes aluminum oxide and 2 ions. And when you look in the appendix, you can read off what the standard enthalpies are. So the standard enthalpies of formation for aluminum, let me actually see if it's in the table or not. It should be right at the top. Yeah, it is. It's the first line of the appendix. It just says 0. It's 0 because aluminum is a metal, which means it's a solid. And this is how it exists in nature. Because it exists that way in nature, it did not require any energy for you to make it, because it already exists. So it has a standard enthalpy of formation of 0. Now, iron oxide is not an element. Elements get to be 0 if they're in their naturally occurring form. And aluminum is a solid. But iron oxide is not an element, so it will have a value of negative 824.2. And that's in kilojoules per mole. These are all in kilojoules per mole. And then the aluminum oxide is negative 1676 kilojoules per mole. And the iron is a big fat 0. Because again, iron is an element. It's on the periodic table of elements. And this is you asking about iron as a solid. So this is how it comes to us delivered by nature. Value is 0. Here's the equation we're going to use. The heat change, the enthalpy change for this reaction at standard conditions is equal to, math symbolism right here. That's a sigma. This is a capital sigma. And all that capital sigma means is sum. You'll know what a sum is, right? Take the numbers and add them together. N gets to be the number of moles, and then delta HF standard of the products. So I'm going to look at my balanced reaction. I'm going to identify which of the materials on the page are reactants. I'm going to see how many moles there are of that. Multiply the number of moles by the delta HF and then add them all up together. And then I'm going to subtract from that the sum of all the numbers of moles of the product of the enthalpies of formation of the reactants. Okay. Let's get you started. So what that means is on the product side, I have 1 aluminum oxide. Plus I have 2 ions. And then I'm going to subtract from that 2 times the enthalpy of formation of aluminum plus 1 time the enthalpy of formation of Fe2O3. Okay. This gets to be 1 times 0 is 0. No. Wrong one. 1 times negative 1676 plus 2 times 0. I have 2 ions. They're both worth 0. I have 1 aluminum oxide. It's worth this number. So things that we see people do wrong on a test. They set everything up, and then they use this set of numbers here. No, you use that set of numbers here. You use this set of numbers there. Otherwise, you get the wrong way, or you get it the wrong way around. Okay. 2 times the enthalpy of formation of aluminum is 2 times 0 plus 1 times negative 824.2. Okay. So things that you are likely to do wrong on this as a test question. First thing you're likely to do wrong. Read the wrong thing from the table. Lots and lots of, so this is going to be in very small print, and lots of these look like each other. There are times when it'll say in your reaction equation, H2O. Well, this table has H2O on it 3 times. Once for ice, once for liquid water, and once for steam, because they all take different amounts of energy to make, okay? And it is very common for people to just read the wrong line. We see it happen all the time. We see people mistake carbon dioxides for carbon monoxides. We see people mistake steam for water. Be careful. It's only a piece of paper. You can write on it. You can take a straight edge and say, that's the number that I need to read. That's the number that I'm finding. Okay. The second thing is, after you've written it out and you've assigned the numbers to individual components to the reaction, is that you use them the wrong way around. This is products minus reactants. And then the last thing that happens is there's an awful lot of negative on the page. I got negative 1676 here. And I've got negative 824.2. All right. So some things in life are easy. If you have a positive number and you add another positive number to it, your answer is more positive than you started with. A positive plus a positive makes a bigger positive. A negative plus a negative makes a larger negative number. But a negative minus a negative, that makes a smaller negative number, okay? Because a minus and a minus is kind of the same thing as a plus. So just make sure that when you're doing this, that what you're saying in your head is, like, I understand the number that the calculator is giving me. I've got 1676. That is a large negative number. And I've got negative 824. That's a smaller negative number. If I subtract a smaller negative from a big negative, I should get a smaller negative answer. So my answer should still be negative, and it should be smaller than the largest negative number that's on the page. And if your calculator gives you anything other than that, clear it and do it again. What's my answer here?
It was 851.8.
It has a direction, it has a magnitude, and it has a unit. Okay? This kilojoules belongs to the entire reaction. We don't write kilojoules per mole for a reaction, because if we wrote kilojoules per mole, the question would be, does that mean per mole of the iron oxide? Or does it mean per mole of the aluminum? Okay, can you see how that might be confusing? But this reaction, as written, gives out 852 kilojoules of heat. Okay? All right. Before we move on, what's the oxidation state of that aluminum metal? Yeah. It is 0 because it's an element. What is it here? In aluminum oxide, Al2O3. Remember? Oxides are O2 minus. That aluminum has gone from being in an oxidation state of 0 to +3. What has happened to the aluminum? What chemically has just happened? Did it gain electrons or did it lose electrons? It's more positive, and electrons are negative, which means it gave its negatives away to become more positive. And what is the loss of electrons called? Yeah. So that just got oxidized. What about the iron? What was the oxidation state of the iron here? So if you can do Al2O3, you can do Fe2O3. Because Fe2O3 is exactly the same thing. I have 3 oxides giving me 6 minuses total, which means in the 2 ions that are present, I need 6 positives. That's a 3. So this went from being a 3 plus down to its element, 0. It went the opposite way. Did it gain electrons or lose electrons? Gained electrons. That's reduction. When something is oxidized, something must be equally and opposite reduced. All right. Oxidation is the loss of electrons. It makes the oxidation state, or the oxidation number, become more positive, larger positive numbers. And of course, because you can start with a negative number for oxidation states, going from -1 to 0 is still an oxidation. Okay, let's do another one. I'll leave that for a second. We are going to do question 7. And when I say we, I do of course mean you. Question number 7's got more coefficients in it, it's got more numbers. Is it any more difficult? Well, it's got more numbers in it, but I don't know that just physically having more numbers in it makes it more difficult altogether. I will write question number 7 on the board. Question 7 says, for ammonias as gases, now ammonia could be a liquid. There's a chance that there's a liquid ammonia in your appendix. Don't use that one. Make sure you're using it in the gas phase. Plus 7 oxygens makes 4 nitrogen dioxides. That's an N. Plus 6 waters. Oh, that was easy to misread. Those 6 waters are steam. Okay, this would be an easy one for you to read this as an exam question. Look in the appendix, scan the table, and write the wrong number down. That's steam. Okay. The standard enthalpy of formation of ammonia gas is negative 45.9 kilojoules per mole. Oxygen as a gas, because it's an element in its naturally occurring form, has a value of 0. Nitrogen dioxide is plus 33.2 kilojoules per mole. And steam is negative 241.82 kilojoules per mole. It is often the case that the tables give you data that have different numbers of significant figures in them. Use them all. Use them all, figure out an answer, round the answer at the end if you must. Use the same process. You have one equation. Figure out what to do with the numbers.
Four times 33.2. Where would you find it?
Do we have numbers? Got final answers? What's your final answer? Anybody else got a final number? What's your number? Good? Yeah? Good? Oh, lots of decimals there. Not sure we're going to allow all of those to stay. Anybody get an answer that's not a negative number? Good. Yeah.
How would you decide what decimal place to go to?
All you're doing is adding, right? So the rules for significant figures when adding is you are allowed to keep the decimal place of the data point with the least number of decimal places, which means this has one decimal place, that has one decimal place, this has two. Our rules for adding and subtracting are slightly different than they are for multiplying and dividing. We keep the decimal places. So I get to keep one decimal place. Okay. The enthalpy change for this reaction under standard conditions should be, look at the products. I have 4 NO2s and I have 6 steams. I'm going to make sure that says steam. And then I'm going to subtract from that 4 ammonias and 7 oxygens. So this is 4 times plus 33.2, okay? Plus 6 times negative 241.82. That's going to be a big deal in this equation. That's going to be a lot of negative. A lot of negative numbers right there. Small number of positives, lots of negatives. I'm going to subtract from that 4 times negative 45.9 plus 7 times 0. Okay. Do we have what these numbers broke down to? Has anybody got it all written out line by line? Go. What was he?
Negative 1,380.12 minus negative.
Is that everything? No.
Yes.
Yeah.
And then minus 183.6.
Okay. So I have a big negative number, and I'm going to subtract from it a smaller negative number. This is like adding a number to a negative. It's going to make my answer less negative than the largest number that's currently on the board. And this should come out as negative 1134 kilojoules. Okay. There are 3 of these on the worksheet. We just did 2 of them. Okay. That's all I've got for you today. What we're going to do Friday, new chapter. We're going to talk about, we're going to revisit electrons, and we're going to convince ourselves that no 2 electrons are identical to each other. Every electron is unique. That means they need their own labels, and we're going to label the electrons in a unique fashion. Okay? None of Friday's work is on the exam. Not on exam 2. The cutoff for what goes on exam 2 just happened. What we start Friday is before the exam, but it's not material that will be on the exam. This weekend. Better not be out of town this weekend. You got a home game tomorrow.
Next home game. Oh yeah, the exam's not on the calendar.
It will.
Okay.
It was like, give me 30 seconds. Are you sure it's not on the calendar? Yeah, okay. Thank you.